Okay, welcome to Unit 1, Lesson 9. What's the equation practice problems? Okay, a party will have hexagonal tables, that means six-sided, placed together with space for one person on each open side. All right, so the first table has six sides, but what happens when you have table 2, you have to leave this side. You have to leave this side open and this side open so you can add another table. So we can only add 4 people. That's what's kind of weird. So if we can only add 4 people every go round, then we have was an arithmetic sequence. Okay? So you have to leave this side and this side open. You have to leave those sides open so you can put another table. The first table is just by itself, so all people can sit at all 6 sides. You would think that you would add 5 on the second one, but that is not so because you need to add on a third. So the tables go on the sides, okay? All right, so now, describe how the number of people who can sit will change by step. So we can make so we're adding 4. Let's see. Oh, C and D. All right, here's C and D on this slide. I'm sorry, I was looking at C and D. Explain why P of 3.2 doesn't make sense. Your inputs have to be whole numbers because you cannot have 3.2 tables. And now we need a recursive definition and an explicit definition. So this starts at 1. So watch our definition. It does not start at 0. So P of 1 equals 6. P of any tables is our previous term plus 4 for n greater than or equal to 2. Okay, we're good with recursive definition. Nth term definitions, explicit definitions. Okay. P of n is equal to 4 to the n minus 1 plus 6 for n greater than or equal to 1. Because I'm starting at 1, I need my first term, and then my change is here. I need my previous term goes with my change. Here's the difference in explicit sequences. Your change and your previous term go together. Okay, let's look at our next problem. Diego's making a stack of pennies. He starts with 5 and then adds 1 at every time. A penny is 1.5.2 millimeters thick. Complete the table with the height of the stack h of n after n pennies have been added. Okay. Complete the table. So let me move this over a little bit so I can complete the table. Okay, so adding 1.52 gets me to 9.12, gets me to 10.64, and gets me to 12.16. So now, does h of 1.52 make sense? This is an input. 1.52 is the size of the penny. It does not make sense. You can only add a whole number of pennies. You cannot add a non-whole number of pennies. So that does not make sense. 1.52 is the thickness of a penny. It's not an input. All right, a piece of paper is 80 square inches. So now look, we're starting at 0. So this is going to make a neat explicit term. A person cuts off 1/4. The second person cuts off 1/4. A third person. So everybody's cutting off 1/4. Complete the table A of n. We want area, so be careful here. After the person cuts off, not what is cut off, but What is the remaining paper? What's left? Not what's cut, what's left. So if you have one whole piece of paper and you take off 1/4, then 3/4 is left. So because 1 equals 4/4. That's 1, right? The same number divided by itself is 4/4 minus 1/4. This is what's cut. This is what's left, 3/4. So 3/4 is left each term. So we're actually, our change is 3/4. So be careful about that one. So your change is 3/4 times 3/4. So they want explicit definition. So we start with our first number, 3/4 to the n power, as long as n is greater than or equal to 0. So let's write n greater than or equal to 0. If n was greater than or equal to 1, we would have had n minus 1 as the exponent, but this is good. I like explicit definitions when we start at 0. And now that you got the equation, you put it into the calculator and you put in the terms. Okay, what's a reasonable domain? Now, if you put this in a calculator into y equals, if you hit the y equals at the top left, put 80, 3/4, 3 divided by 4. Let me write that differently. Make sure you write the parentheses. Close the parentheses. Over the 8 and 9 are the parentheses. Caret, this button is over the division symbol on the right. And then you put xt theta n, which is next to the green button on the left. Put this in the y equals. Then go second table and read the list of numbers. Now, your domain is going down x. So you're going to start at 0 and you should go in whole amounts. Well, how far do you go? You have to take off 0. Less than x is less than or equal to some upper limit. Whatever you come to, about 15 cuts, you get about 1 square inch left. Anything smaller than an inch, it's hard to cut off 3/4 of it. You might want to go further. I don't know. So a domain is a range of reasonable numbers. Okay, next problem. Here is a recursive definition. 35 minus 8 is 27. So 35 minus 8 is 27, minus 8 is 19, minus 8 is 11, minus 8 is 3. And so now let's graph this function. 35, this is term 1, not term 0, so term 1. 35, then 27, then 19, then 11, and then 3. And as we can see, I gotta move this over just a touch. And as we can see, this makes a straight line. So arithmetic sequences are linear. How do I know it's arithmetic? Minus 8 is the change. Okay, wait, here's a graph of the sequence Q. Let's define it recursively. So the first thing we're gonna do is we are going to find the numbers. So 1, 2, 3, 4. So this is -3, 0, 1, 2, 3, 3, 1, 2, 3, wait, 4, 5, 6, 7, 8, 9. Okay, so this is going up by 3. So this is plus 3. So our first term is 1. So Q, sugar. Q of 1 is -3. Q of any term equals the previous term plus 3 for n greater than or equal to 2. Because we started at 1, our next term needs to be greater than or equal to 2. Okay, now look at this one. So this one has f of 0. F of 0 equals 19 minus 6. How do you know these definitions represent the same sequence. Now, this is the recursive. The top one, the purple one, is recursive. All of it is recursive. The second one is an explicit definition. And how do I know it's explicit? Because we don't need n minus 1 because it is starting for n. The next term is n greater than or equal to 0. If n was greater than or equal to 1, that means our first term would be 1, and this one would be n minus 1. So it's the same sequence. They both start at 19, and they subtract 6. Now, select a definition to calculate f of 20. All right, so f of 20 is an input. I would choose the explicit definition. Why? So if we calculate it, we get 19 minus 6 times 20, and it's just a simple calculation. For 19 minus 6, I would have to write term 1, term 2, term 3, term 4, term 5. I would have to calculate it 20 times, well, 19 more times, because the 0th term is 19. And I could just do 19 minus 120, because 6 times 2 is 12. And 19 minus 120 is negative 101. Explicit terms are good for finding any term in the sequence quickly. Recursive definitions are good for finding the first numbers in a sequence. Okay, an arithmetic sequence, we see the word arithmetic, and we're going to write plus minus. Okay, goes from 20 to 16. I'm subtracting 4. I would use an nth term definition. So I'm going to start the blue one at 0. I'm going to call this term 0. So my J of any term would be 20 minus 4 to the n, as long as n is greater than or equal to 0. If I wanted to start J at 1, if I want to call this term 1, which I'm going to color green, J of n would be 20 minus 4 to the n minus 1, previous term, for n greater than or equal to 1. Okay? So whichever one you want to use, I like the blue one better. These are both explicit. So for J of 500, I just stick 500 into either one as the input. I stick it in for n and into either one. I calculate it, and that's how you get the term, the 500th term.